working now, isn't it?
Yes.
Okay, sorry for that. So, yes, some introduction and motivation. So about 25 years ago, as you well know, Strominger and Vafa succeeded in giving a quantitative and microscopic interpretation of the Bekenstein-Hawking entropy of at least a class of black holes in string theory, answering one of the key questions in quantum gravity. And following up on that, going beyond leading order in the large charge regime, there was a lot of work trying to compute subleading corrections to the black hole entropy, both from the macroscopic side and from the microscopic side at increasing level of details. And while this has uncovered a number of new physical phenomena, for example, wall crossing phenomena, and also brought out new connections to mathematics, for example, to enumerative geometry and the topic of modular forms and mock modular forms. So in the case which is best understood, which are string vacua with n equal to 4 supersymmetry, the exact number of BPS black hole macrostates is now known for any charge vector gamma and any moduli t. So the dependence on the moduli is important precisely because of this wall crossing phenomena. And it's given in terms of Fourier coefficient of a particular number theoretical object, a Siegel modular form for n equal to 4 supersymmetry, or Weak-Jacobi form for n equals to 8. I should say this is not quite the exact number, but the sign number, so that's the index, which is sensitive to short multiplets and where long multiplets can cancel. So this goes back to DVV, Digraphen and Defrender in '96, who proposed the formula. And then there were subsequent work to put this guess on the solid basis from the microscopic side, work by David Sen, who basically reproduced it as by counting D1, D5 Kaluza-Klein monopole bound states. And from the macroscopic side, there was a lot of work. I cannot quote all authors, but on the supergravity partition function or entropy function computed using localization. And the agreement has been spectacular, up to exponentially suppressed corrections at large charge, which are actually very specific to the mock modular nature of this counting function. So that's the physical story. As for the mathematics, the BPS indices, which count these BPS states, can actually be defined in a rigorous fashion, and they correspond to generalized Thomas invariants of the Calabi-Yau. So here we're talking about type 2 on K3 cross T2, which is a rather particular kind of Calabi-Yau, but nonetheless you can define these invariants, and the complete agreement has been found, although as you can see, the mathematicians are about 5 to 10 years behind the physicists in this story. Now, my main interest or goal is to try to develop a similar story for the case of n equal to 2 string vacua, namely type 2 strings compactified on a compact Calabi-Yau threefold, where the precision counting of black hole microstates is much less advanced. Part of the motivation it comes from mathematics, since the Thomas invariants which control these indices are much more subtle to define and to compute, and also some of the physical phenomena are more complex, as I mentioned in a second. So there has been some basic understanding of this problem already going back to 1998, work of Maldacena, Strominger, and Witten, who explain, at least for the case of D4, D2, D0 bound states, how to interpret them or construct them microscopically as wrapped M5 branes in M theory. And those 5 branes wrap to a 4 cycle. If you reduce the 2,0 theory on the word volume of 5 branes on that 4 cycle, you get superconformal field theory in 2 dimensions, for which you can compute the central charges, and using the Cardi formula show agreement with macroscopic in the large charge regime. But unlike the case of n equals to 4, there are very few cases where you can actually compute the exact BPS indices. There is one notable exception, which is the work by Garrito Strominger Yin in 2006, who used the modular symmetry coming from the superconformal field theory point of view to compute the sum of these invariants for a single D4 brane, but the general story is still wide open. And so part of the difficulty is that these BPS indices depend on the moduli, so the asymptotic value of the moduli at special infinity in a very intricate way due to this wall-crossing phenomena, which in the case of n equals to 4 were only associated in the appearance or disappearance of two centered bound states. But for n equals to 2 can involve an arbitrary number of centers. So you have to understand the quantum mechanics of these multi-centered solutions if you want to disentangle their contributions from the real spherically centered black holes for which holography applies, for example. So in general, we expect along the lines of MSW, Vafa-Witten, that the generating function of these BPS indices are denoted by HP of tau, where you fix the D4 brane charge, the D6 brane charge is set to 0. You can also fix the D2 brane charge, and you sum over all possible values of the D0 brane charge with some parameter e to the 2 pi I tau conjugate to n. So we expect this generating function to be related to the elliptic genus of the superconformal field theory, and therefore to have some kind of modular property. But in fact, it cannot be strictly modular covariant because of wall crossing, except in cases where the divisor or the force cycle, which is right by the 4 brane, is irreducible. So that was actually the case that Gayotto, Strominger, Yin considered. It's the simplest case, but it's not the full story. And so in some recent work with Sergei Alexandrov, Sebashish Banerjee, and Jan Manshot, we have studied this problem and characterized the modular anomaly of these generating functions in the case of type 2 theories compactified on Calabi-Yau threefolds. So we explained that this generating function cannot be modular and holomorphic. So if you define it as a manifestly holomorphic object, it cannot be strictly modular. But it has a modular anomaly, which is expressed in terms of the generating functions associated to the constituents of the bound states. In other words, if the D4 brane charge can split into a sum of positive D4 brane charges, the modular anomaly HP will be controlled by the product of the HPIs for each of the constituents in a kind of recursive fashion. So that gives a very precise, I won't go into the details of this in this talk, but it gives a very precise prescription for the modular properties of the generating function. In principle, one can use it to bootstrap the exact numbers from computing a few low order coefficients, for example. Very good. So the way we arrived at this prescription was to study the implications of modular invariants. Well, actually not so much at the level of the superconformal field theory, which is not very well understood, but in terms of the moduli space of type 2 theories, once you compactify them from the Calabi-Yau down on another circle, down to 3 dimensions. And if you require the moduli space in 3 dimensions to carry an action of S duality, SL2Z, basically either coming from type 2B, SL2Z, S duality in 10 dimensions, or coming from the SL2Z of the 2 torus in M theory on Calabi-Yau cross T2. Then you can put some constraints on the metric on this moduli space. And since some of the instanton corrections to that metric come from black holes in 4 dimensions, which run around the circle, you can actually constrain these contributions and specify the modular anomaly, or in fact the holomorphic anomaly of a certain completion of HP, which I will discuss a little bit later in the talk. So this is very well in the sense that we have good control on these generating functions for arbitrary compact Calabi-Yaus, but at this point we don't know how to compute them explicitly because it's hard to compute the basic indices from which you could bootstrap the full answer. So this talk will be on a somewhat different topic. It will be on the case of counting D-brane bound states in the case of local Calabi-Yau compactification. So we consider type 2 string on the local Calabi-Yau, which is the total space of the canonical bundle over some complex surface S. So the canonical bundle is a U1 or a C star bundle over the surface. So it has a complex dimension 3, but it's non-compact along the fiber direction. And in that case, so the states that we're interested to count are D4, D2, D0 bound states, which wrap the surface. So in fact, you can express the BPS index in terms of quantities which just depend on the surface itself. Namely, the index in that case is basically the Euler number of the moduli space of stable Coherent sheaves, which describe these 4 branes with their gauge bundle wrapped on the surface. And we'll mostly talk about Fano surfaces. They are surfaces with the positive curvature, which can appear at singularities in the moduli space of compact Calabi-Yaus. So the story should be more general. So one reason to be interested in this is that these numbers also have a significance as Vafa-Witten invariants for the topologically twisted n equal to 4 super-Yang-Mills theory on the surface S itself, with the gauge group UN if the D4 branch has n units of charge along this 4-cycle S. And here, S duality comes from, or modular invariance can be traced to the S duality of n equal to 4 super-Yang-Mills, which of course is related to the modular symmetry of the superconformal field theory by taking the product of the 4D times 2D theories inside the 2,0 6-dimensional theory of the 5-brane. And so again, the same constraint imply that the generating functions should be Mach modular for Vafa-Witten invariance with the gauge group UN. And our previous work on DT invariance on compact Calabi-Yau basically implies the holomorphic modular holomorphic anomaly equations for the Vafa-Witten invariance, at least in the case of complex surfaces. Equations that were conjectured already a long time ago by Minahan and friends. So that's our main motivation. In fact, is to understand precisely the consequences of modular anomaly or Mach modularity in this context. So the main technique that we'll use will be quivers. In other words, the equivalence between the derived category of Coherent sheaves on this Fano surface S, which count D4, D2, D0 branes, as some kind of bundle on the surface, and the category of representations of a certain quiver, which is associated to the surface. So this is a well-known story. Was developed already in the physics literature in early 2000 and goes back earlier in the math literature. And just to flash an example here for local P2, the canonical bundle over the complex projective space, the quiver is this 3-node quiver with 3 arrows going between every pair of nodes, which you recognize as being the quiver describing the Z3 orbifold singularity in a non-compact Calabi-Yau, which is in fact a particular point in the moduli space of local P2. In general, there is such a description for arbitrary surfaces, and I'll explain a bit how that goes, where the nodes of the quiver correspond to a so-called exceptional collection of sheaves on the surface. So that translates the problem of computing BPS indices or Vafa-Witten indices into computing the Euler number of the moduli space of quiver representations, which now depends on the dimension vector. So that is the rank of the gauge groups that you associate to each of the nodes here, as well as some phi Iliopolos parameters, both of which are determined from the charge vector, D4, D2, D0 charge, on the moduli of the Calabi-Yau. Now, the two problems are equivalent, and one is not simpler than the other. except in some special cases. One simple case would be if the quiver had no loops. That's not the case of the previous one. And in fact, it's never the case here. So let's forget about it, unfortunately. The other simplification, which is relevant here, is that, as I explained, the quivers which come from Fano surfaces are quite special. There is one chamber where the index is entirely determined. The chamber is we call it the attractor index, the attractor chamber. So there is a particular choice of Fayet-Lopoulos parameters depending on dimension vector, which is in fact the analog of the attractor chamber in supergravity. And what we'll show, that's basically the main result of this work, is that in this chamber, the attractor indices are all zero, except when the dimension vector is supported on a single node, namely only there's a U1 gauge group, there's only a U1 gauge group, or the other ones are spectator. So that's quite trivial, omega star is 1. And less trivial is when the dimension vector corresponds to D0 branes. The point is that D0 branes can probe the full Calabi-Yau, not just the surface, and they are so they're somewhat different. But fortunately, we don't need to invoke them to compute the other indices. So in fact, knowing these indices in this particular chamber, we can get them everywhere else that we wish. One way would be to follow a sequence of wall crossings, but the more expedient way is to use the so-called attractor flow tree conjecture, or which was put forth by Denef, Green, Rogas in 2001 from the supergravity point of view, or a more explicit and an algorithmic version of it, which we call the flow tree formula, which we developed with Sergey a couple of years ago, which allows to express this BPS, the BPS invariant for quivers at arbitrary value of Fayet-Lopoulos parameters in terms of these attractor indices. Basically, as I explain later, omega will be a sum of products of these constituents associated to various trees. Anyway, I'm just surveying right now the main idea, and I'll go into details very soon.
Excuse me, Boris.
Yes, please.
I'm confused with the terminology attractor value of the moduli because it's local Calabi-Yau, so it doesn't have black holes, right? Am I right?
That is right. So
so it's not the black hole attractor concept, or is it a generalization?
Nonetheless, you can define. Yeah, it turns out you can define an analog of attractor flow for quiver quantum mechanics, which is kind of a discrete analog, and you can still, as I explained, represent the BPS spectrum of quiver quantum mechanics at any point in terms of bound states of such constituents, in such a way that in this particular chamber, that no bound states contribute at all. So you have in that chamber, you're only left with some number of BPS states, which is not large enough to create a black hole, but which is nonetheless the analog.
So here is just a convenient fiducial point, starting from which you can construct more.
Yes, well, in fact, I'll explain the precise sense in which it corresponds to the attractor point on the Calabi-Yau side later.
Okay, thank you.
Very good. So yeah, in fact, that was the next sentence here, that the large volume. So the large volume attractor chamber on the Calabi-Yau side, even which is well defined even for local Calabi-Yaus, it turns out not to correspond to the attractor chamber on the quiver quantum mechanics, where you would not expect to have any. From what I said, there would be no BPS states, because I just said that omega star was 0. But in fact, it corresponds to the anti-attractor chamber, where the Fayet-Lopoulos parameters have the opposite sign. And therefore, it is a point where there is a rich spectrum of BPS bound states. And those BPS bound states correspond to the D4, D2, D0 states on the Calabi-Yau side in this large volume attractor chamber, which, by the way, is the chamber in which we expect that the BPS indices have modular properties. So that's a little kind of paradox, which I hope will be resolved by the end of the talk. And well, one interesting consequence of what I just said is that the modular properties of Vafa-Witten invariants translate into modular properties of these geometric functions of quiver indices, or mock modular properties rather, which I think is the first example where we can see a class of quivers for which joining functions have modular properties, and hopefully there will be a simple way to understand these properties from the quiver point of view. Okay, so that's basically the overview and summary of my talk, and the rest of it will be to explain some background about how to go from surfaces to quivers, how to compute BPS indices from attractor indices, as well as from, although a similar related notion, which is a notion of pure Higgs indices, and I'll explain how the method works in simple examples. So maybe I should pause again for questions.
Oh, yes. Boris, may I ask a question?
Yes, please.
Oh, so I was just wondering which part of this contents in the previous slide is specifically for this anti-canonical bundle over the Fano surfaces. So the flow tree mechanism would work for any local Calabi-Yau?
So the flow tree formula works for any quiver quantum mechanics. It's basically a general solution of the wall crossing formula of Concevi-Zolbermann. It's constructed such that it agrees, it provides the correct answer in the attractor chamber and is consistent with the wall crossing.
So you don't
now,
even
in the case, so yeah, you work for any local Calabi-Yau, I think, whatever Fano surface or not. In the context of compact Calabi-Yau, it's somewhat more subtle because you have to check some stability conditions on the trees, make sure that the splitting takes place at really walls of homogeneous stability and not anti-walls, but that's automatic in the context of quiver quantum mechanics. Does that answer the question?
Thanks.
Thank you.
Can I ask you one more?
Yes, please.
Grace?
Yes.
So this omega star that's in this particular chamber, I mean, will it enter like omega S, the single center one, or is it different one?
No, it's two different notions.
Two different
I'll explain
Good.
how they are related, but basically, so omega star counts not only single-centered black holes or BPS bound states, BPS states, but it also would get contributions from so-called scaling solutions. And what I show is that in these quivers coming from Fano surfaces, in fact, there are no scaling solutions. So omega star is equal to omega S, but it's a very specific property of these models. And it's also somewhat puzzling because classically you see there are scaling solutions, but quantum mechanically the claim is that they are removed.
Thank you.
Very good. So let me now proceed with some details. Okay, so I want to explain a bit how to go from the geometry of Calabi-Yau to quivers, although this is a very well-known story, but it may be useful for some of you who are not working on this. So first of all, I said D-branes are described by coherent sheaves, which is more a vector bundle whose fiber dimension may jump. If the fiber dimension is non-zero over the whole Calabi-Yau, then you describe a D6 brane. If it jumps on the divisor, it corresponds to a D4 brane. On the curve, corresponds to a D2 brane, and then it could jump on the point, and that's a D0 brane. So, but that's the appropriate mathematical language. So D-branes carry charge, which correspond to the Chen character of the vector bundle or the sheaf. Namely, the rank is the D6 brane charge. First Chen class is D4 brane charge. Second Chen class is D2, and third is D0. So the spectrum of open strings between those D-branes is governed by what is called the global extension group, which I won't go into the detail of it, but just need to notice that it depends on the pair of D-branes E prime and some integer k. So for k equal to 0 corresponds to tachyonic open strings, except when E is equal to E prime, in which case they are removed by GSO projection. k equals to 1 is it corresponds to nearly massless states that would be strictly massless at some orbital points. And then k bigger than 2 is irrelevant because those are the strings of order Planck scale. So we're interested in the dynamics of this nearly massless states, and want to make sure that there are no tachyons. So this would be for D-branes on a full Calabi-Yau, but for a local Calabi-Yau, we're interested in D4 branes supported on the surface itself. So you can basically get them, the Coherent sheaves, by lifting sheaves on S to sheaves on X. So I denote this operation by I star, some kind of embedding map. And the point is that these groups on the Calabi-Yau are X are given by the global groups on S for weight K, index K, and index 3 minus K. So you see that the light open strings on the Calabi-Yau originate both from X1 and X2 on the surface, whereas X0 and X3 would correspond to tachyons. Now, how do we compute these groups? It's generally quite complicated, but at least it's easy to compute some linear combinations of dimensions via the so-called Euler form. So it's an alternating sum of dimensions of xk. And this is related to some index theorem. So there is some Riemann-Roch formula which allows to compute it for any pair of sheaves, just depending on these Chen characters. And here's the formula. You see it only depends on the product of ranks and instanton number CH2, etc. The first line here is symmetric, whereas the second line is anti-symmetric. And the degree here is notation for the product of the first Chen class of the sheave, which is the D2 brane charge, times the first Chen class of the surface. So now stable D-branes correspond to the subclass of Coherent sheaves, which are stable, or more precisely Giesecker stable. So this is a little bit technical, but let me mention it nonetheless. So a sheaf is stable if is slope stable, if all proper subsheaves have smaller slope, where the slope is defined by the ratio of the degree, or the product of C1e times the Keller form on the surface over the rank. So here you already see some dependence on the moduli of the surface entering. And well, if it's equal, you have to refine this notion. That's what is called Giesecker stable. You have to put some condition on the ratio of second Chen class. That's actually necessary to have a nicely behaved moduli space of sheaves. So if you fix the Chen vector gamma and look for all such Coherent sheaves, it will have a dimension. Well, it will be a smooth projective space, at least if gamma is primitive, whose dimension is simply expressed in terms of this Euler form, actually only the symmetric part of the Euler form. Well, this is typically negative, so the dimension will be positive. And when the dimension is strictly negative, then you conclude that the moduli space is empty. So the important point here is that this moduli space is invariant under a simple operation, which we call spectral flow, which amounts to shifting the first Chen class by by n times the n being the rank, the Chen class of some line bundle. In other words, you only need to consider a first Chen class modulo n times the relevant lattice, the rank being invariant under this operation. Okay, so now, so this is how do we construct a set of basic D-branes from which we can read off the full spectrum. So that's the technology of exceptional collections. So first of all, an exceptional sheaf is a rigid sheaf. So it's one where in particular the dimension is 0 and the number is 1. And technically you require that all the xk groups are 0 except the x0. And as I said before, this is not a tachyon, it's removed by JSO projection. So that's one of them. You want as many of them as to generate the full lattice of charges. So you want an external collection is a set of such sheaves where the xk groups vanish unless I is less than j. In other words, this Euler matrix is upper triangular. with ones on the diagonal. The one is just the constraint that each of them is an exceptional sheaf. Like this. And so you should choose as many of them as to span the lattice of charges for simply connected surface S. The rank of the lattice is just the Euler number, is the number of 0 cycle plus 2 cycles plus 4 cycles. There's only 1 4 cycle and 1 0 cycle. Now, in addition, we want to have this no tachyon condition, and that's actually somewhat tricky. It was analyzed in these papers a long time ago, where it was understood that to construct such exceptional collections, you have to start from some dual collection which satisfies some strong and cyclic property. Dual means that the Euler number of EI times this dual E check J is delta IJ. And I don't want to go into the detail of that story. I don't have time for this, but there is some mathematical way of generating these strong cyclic exceptional collections from which you can read off the one which is really relevant for the quiver. One point is that you really need the technology of derived category, because whereas these dual sheaves can be proper sheaves, the ones that we require for the quiver may well have negative rank, so they really live in the derived category of current sheaves. In other words, they can be algebraic sums of sheaves with the sign plus and minus. Good. So now, having this collection, we can construct the quiver in the usual way. So for each member of the collection, we have a node, which is a vector multiplet in quiver quantum mechanics in a 0 + 1 dimensional supersymmetric gauge theory. And then we have charge matter in bifundamental coming from these X1 groups from EJ to EI. And well, we have in addition constraints. So those are, I write them as morphisms, but these morphisms, you can think of them as being chiral multiplets. And then there are constraints corresponding to the X2 groups going in the other way. But physically, we can think of those constraints as coming from F-term equations from a certain superpotential, which depends not only on the chiral multiplets from I to J, but also mu chiral multiplets from J to I, in such a way that if you take the gradient of the superpotential with respect to this dotted guy, you get the constraint for that one. In other words, we have a quiver with superpotential. And that defines a 0 + 1 dimensional supersymmetric gauge theory, which is usually called quiver quantum mechanics. So rows from I to J is simply expressed in terms of this Euler matrix, and it only depends on the anti-symmetric part of it. And so that is, in fact, the usual prescription that the number of massless open strings is given by the Dirac product of the D-brane charges. And here you notice that it only depends on the rank and on the degree of the sheaves. In particular, D0 branes would have rank 0 and degree 0, so they totally decouple from this. So they live in the kernel of this bracket. And then there can be different choices of collections, which give rise to different quivers related by Seiberg duality. So let me give the simplest example, which is a local P2. So it has a tachyon-free exceptional collection, which is well known in literature, going back to Douglas, Romelsberger, Fjoll for the physics part of it. And you see that some of those sheaves here have negative rank. So here's the rank, first-chain class, second-chain class. And but they come from they come by duality from proper sheaves. And if you compute the ES matrix, you see it's upper triangular. The entries are not necessarily positive, but you can read off the quiver from here. So you see that there are 3 arrows going from 2 to 1, sorry, 1 to 2, 2 to 3, and 3 to 1. And there's also a way to get the superpotential, although it's more technical. But in this case, it's very well known, of course, from the orbifold point. Okay, I'll go back to this example at various points. So now we have this mathematical theorem that tells us the equivalence between this category of current sheaves and the category of quiver representations. which I denote in this way. And basically, I want to explain what is the dictionary from going from one to the other. So recall that on the sheaf side, we have this grading by the Chern vector, which is the D4, D2, D0 brane charges, whereas on the other side, we have the grading by the dimension vector, the rank of the gauge groups at each node. And well, the relation between the two is simply obtained by identifying the Chern vector of the sheaf with the sum of the Chern vectors of the constituents, not each one weighted by the weight. So we have Ni, and physically we have Ng copies of the Ni copies of the D-brane described by this sheaf. There is a minus sign here, which ensures that if we take large D0 brane charge, the Chern vector will be, the dimension vector will be positive. But anyway, there is a symmetry flipping the charge, the sign of the dimension vector. So the next point is to translate the moduli from the Calabi-Yau side to the quiver side. So on the quiver side, we have these phi-Lopulus parameters associated to each of the nodes, and it's well known, probably since Denef's work, that you can relate those to the central charges of the constituents Z gamma I, and the total central charge of the full bound state. Gamma is the sum of the Ni gamma I. Well, there is some unspecified overall rescaling coefficient here. And the central charge in the large volume limit is just basically the volume of the surface times the D4 brane charge, plus the volume or the area of a 2 cycle times the D2 brane charge, plus the D0 brane charge. So that's the regime in which we want to compute this BPS invariance. Now, how do we? Well, okay, is that the right condition for describing coherent sheaves? Well, Giesecker stable coherent sheaves. The answer is yes, because the stability condition requires, well, basically depends on this sum of phi-Lopulus terms times dimension vector Ni for sub-representation. And if you use these formulas and we express it in terms of sheaf data, you see that at large volume, so rho is basically J squared. At large volume, you get the difference of the slopes multiplied by Nn prime. And then there is if those two slopes are equal, there is a subleading correction, which is the difference of the instanton numbers. So this choice ensures that the moduli space of sheaves, of Giesecker stable sheaves, will be isomorphic to the moduli space of quivers with that particular choice of phi-Lopulus parameters. Now we can check by looking at the dimension of the moduli space. So recall that on the sheaf side, the dimension was 1 minus chi. So if we express this Euler form in terms of the entries the entries here, and split into positive entries and negative entries, and those on the diagonal, which were all 1, you recognize exactly the dimension of quiver moduli space in a branch where the arrows from I to J, whenever this is negative, have non-vanishing expectation values, whereas those going from J to I have vanishing, but correspond to imposed constraints corresponding to the gradient of the superpotential. And then this subtraction is, of course, dividing out by the gauge group action, except for the center of the gauge group, under which all fields are neutral. In other words, there is a particular branch in the quiver, which we call the Baylissen branch, where all those dotted arrows vanish and the moduli spaces agree. And that requires some particular choice of slope, which I don't want to go too much into. So let me illustrate this on the case of local P2 once again. So I recall the quiver and the superpotential. So if you use the data I gave for the sheaves associated to the nodes, you see that the dimension vector N1, N2, N3 is given by these 3 components. In particular, it's worth noting that the pure D0 brane corresponding to CH2 being non-zero contributes 1 unit to each of the ranks at each point. Whereas the Fayet-Lopoulos parameters in this large volume chamber will depend on differences of the ranks, plus some subleading correction. Now let's check that the dimensions agree. So in this under this superpotential, there is a chamber where all the arrows going from 3 to 1 vanish. You have only those going from 1 to 2 and 2 to 3. The dimension, therefore, will be 3 times n1 and 2 plus 3 and 2 and 3 minus 3 and 3 and 1 from the constraint, and that indeed agrees with the dimension of the moduli space. However, that's only possible if you can set those arrows to 0. So you require that zeta 1 should be positive, zeta 3 should be negative, and that requires some constraint on the first jump class. Okay, so is that, are there any questions at this point?
I'm afraid I missed n without any subscript.
Yeah, the capital N is the rank of the sheaf. So it's the D4 branch charge if you want.
I see. Thank you.
Not to be confused with the NIs. Now I lost track of the time. I think I have 15 minutes left, right? Something like that. Okay, so under this equivalence, we can translate the two problems, and so the BPS index for D4 branes is now the BPS is given by the Euler number, as I mentioned previously, of that normalized space. It turns out to be useful to refine this notion to the Poincare polynomial, which is a weighted sum of Betti numbers depending on the parameter y, which reduces to the Euler number as y goes to 1. That's usually ill-defined for compact calabia, but it's perfectly well-defined and robust quantity for local calabias. And well, if it's also useful to introduce a variant of that, which is rational DT invariance whenever the dimension vector is not primitive, because those quantities are simpler under wall crossing. Good. So I was going to say a few things about modularity of partition functions, but I have to be quite brief. So from the Vafa-Witten point of view, you see that if you take the genomic functions of these omega bars suitably rescaled, and you let the instanton number n be arbitrary with some parameter q conjugate to it and some little decoration here, and this should transform as a vector valued Jacobi form of certain weight and index. So Jacobi form because there is this refined parameter y here. But as I mentioned earlier, that's only an expectation. And in fact, if the rank is bigger than 1, that there will be non-holomorphic contributions to the partition function of n equal 4 Yang-Mills, which will make it which will ensure that it's modular but non-holomorphic. So this was in fact understood from a more microscopic point of view more recently in this work by Davoka and Putrov-Witten. The issue is not there for rank 1. In that case, it's truly modular and in fact given by this well-known formula of Götcher. And in fact, so historically, this was how people computed Vafa-Witten invariant on surfaces by well, finding a chamber where those invariants were trivial, and then using sequences of blow up and wall crossings to reach a chamber of interest. And so in particular, the work of these authors. And so in my talk, what I present is an algorithm to achieve, to compute the same numbers, but from a completely different way, and where, however, modular symmetry is not manifest using these quivers. Okay, so for this, we need to understand this notion of wall crossing and attractor indices. So this is, here I'll review some earlier work of mine with Ashok Sen and Anyan Manshot, and more recently with Sergey. So first, remember that the journal, there is a general prescription due to Kontsevich-Zauberman for computing the jump of these invariants across the walls, which we understand physically as the appearance or disappearance of multi-centered black hole bound states. And in fact, you can compute it, the jump from arbitrary number of centers by using localization methods, which allow to compute the number of BPS bound states in this supersymmetric quantum mechanics. And so in this work, we showed that localization basically reduces the problem to counting collinear black hole configurations along the Z-axis, satisfying a one-dimensional version of Denev's equations. Well, so that's for wall crossing. Now, there is one particular chamber which I mentioned plays an important role, which is the attractor point. So in the context of supergravity, is the point which is reached when you look at spherically centered black holes and let the moduli evolve from infinity to the throat. But it turns out that in the context of quiver quantum mechanics, there is a very nice and simple analog, which is to take the product of the dimension vector times this matrix this adjacency matrix kappa ij, which counts arrows going from I to j with plus sign and minus sign from j to I. So the point is that on this particular point, you can show there are never two particle bound states, which is a property that we also know on the supergravity side. And so you can in fact reconstruct the full spectrum from this attractor, from the value of the indices at these particular points. And that's this, the general idea was given in supergravity by these authors, where they proposed to think of general bound states as some kind of hierarchical structure of two particle bound states. So seen from far, you have just a single center, but as you zoom in, you see two centers appearing, and you zoom further, each of them splits into two centers and so on, until you reach a number of constituents, which are each of them in their own chamber of attractor. So that's a nice picture, but you want to translate it into a formula. And so we succeeded in doing this with Sergei. And we basically gave a prescription to construct this index in arbitrary chamber by looking at all possible trees, stable flow trees, which end on all possible constituents for these decompositions. And the claim is that each of these trees corresponds to a class of bound states which contribute to the total index, the product of indices for the centers, times the product, well, the quantity which counts how many bound states are created at each level. So I won't give any detail on how to compute this, but let me just say that you do need to let the moduli evolve along the tree in a way which is similar to supergravity, but it's purely combinatoric. And it's basically a sequence of projections and symplectic projections. And particularly, it does not require integrating the attractor flow as is the case in supergravity. So the formula is completely algorithmic. In fact, it's available as a Mathematica package. And it becomes useful once you can compute these indices here, of course. And here comes the main observation of this work. That is that these invariants vanish unless n is supported on a single node or is proportional to the dimension vector corresponding to pure D0 branes. Now, how do we arrive at this conclusion? How do we prove this? Well, we have a kind of ad hoc proof that works, but we would like to understand it better. But basically, we can exhibit some quadratic form, which depends on the dimension vector, as well as some coefficients, lambda I, which are some rational numbers, such that the dimension of the moduli space of quiver representations in the given chamber is written in this way. So 1 minus q minus sum of lambda I, ni, zeta I star, the attractor values of periodic closed parameters. And this quadratic form is constructed such as that it is positive. So this is almost always negative. And also the signs, these numbers here have the same sign as the zeta I star. So this is also manifestly negative. So this is essentially always negative, except when the dimension vector lies in the kernel of this quadratic form. And that's exactly this direction for D0 brane. Or unless it has only support on one node, and then you have to work a little bit harder to see that the dimension is just equal to 1. So unfortunately, we don't know really where this quadratic form comes from. We look for it on a case-by-case basis, but it's so it's a very simple argument. At least it doesn't require fancy mathematics. And in just a second, I'll show it for local P2. But once we have that, of course, we can use the flow tree formula to compute the index anywhere else. Well, there is a subtlety that we don't know the index for these zero branes, but as I said, they are in the kernel. So in fact, they don't contribute to wall crossing. So that's the first main observation. And the second main observation is that the large volume attractor point for local Calabi-Yau geometries, it turns out to correspond to the opposite of the attractor point on the quiver side. That is, we flip the sign in this relation. So that's actually, as I said, that sounds puzzling at first, because we know from supergravity that multi-centered black holes are not supposed to appear at the attractor point. But apparently, the BPS spectrum at this point can still be described by multi-particle bound states in this quiver quantum mechanics. And the key point is that this first sentence holds at the attractor point, but not at the large volume attractor point where this relation holds. And so the idea is that this microstructure of bound states is revealed as you travel from a large volume to the genuine finite volume attractor point, which would correspond to the attractor point on the quiver side. So that's somewhat well, I think you have to wrap your head around this a little bit, but I think it makes perfect sense. So the attractor indices on the quiver side correspond to one point where all the D4 branes are disintegrated into products of D6 anti-D6 branes, basically, as you cross down to a finite volume. Good, so let me exhibit how this works for local P2. Well, here's the quadratic form that does the job. And as you see, it's a sum of squares, so it's always positive, but it's generate along the direction where all the ni's are equal, and that's the D0 brane charge. And then there is these additional terms, which fortunately are always of the right sign to ensure that the dimension is negative, and therefore the moduli space is empty. So using these observations, we can just use the attractor flow formula to compute the indices in this canonical chamber or anti-attractor chamber, and well, you produce the expected results obtained from other methods in a completely different way. So it's a new way of generating these BPS indices. Which is, I think, entirely algorithmic, although of course it becomes slower and slower as you increase the charges because the rank on the quiver side increases. Okay, so let me take another brief pause if anyone has questions, although I not have too much time. Okay, so if not, let me come to this point that Pijing was raising at the beginning, which is how about single-centered bound invariants? What is their relation to these attractor indices? So as I said, on this attractor point, even though they cannot be two-centered bound states, nor in fact any genuine bound state, they could still be contributions from scaling solutions where several centers come to arbitrary small distance. It's a well-known feature of quiver quantum mechanics with loops, which was explained in those papers. And in some work from about 10 years ago with Ashok and Jan, we actually gave a formula for determining the contributions from these scaling solutions and extracting the BPS index from single-centered black holes. So this was also relying on some independent work by Pijing, some specific examples. So there is a different formula, which we call the Coulomb branch formula, which is conjectural, unlike the previous one, which expresses the total index in terms of product of indices which really count single-centered black holes times an object here, which is similar to the one which appeared in the KS formula. It still counts collinear solutions, but it is suitably modified to include contributions which are some are missing corresponding to these scaling solutions. These solutions don't correspond to any collinear point, but somehow they must be added by hand to make sure that the index is really, the refined index is really a symmetric polynomial in Y. In other words, really a character for the rotation group. So we call this prescription the minimal modification hypothesis. And the claim was that if you, so once you subtract scaling solutions in this way, then the indices here are really count spherically symmetric black holes. In particular, they do not suffer from wall crossing, so they don't depend on zeta. And also they don't carry angular momentum, so they should be supported on the middle cohomology of the quiver moduli space. Well, applying this formula, which again I can't really spell out, we find evidence for the conjecture that similar to omega star, these single-centered indices also vanish under the same condition. And well, basically the way to do this is to evaluate this formula at the attractor point and recursively determine these numbers contributing. And well, as I said, this is surprising because certainly for 3-node quivers with loops, scaling solutions do exist. Well, not only you need loops, but you also need the number of arrows to satisfy certain kind of triangular inequalities. And the point here is that these inequalities are just barely saturated. And in fact, the quantum effects remove this apparent scaling solutions. So it's a very particular property of these quivers, and we certainly don't expect it that it would be true for BPS states on a proper compact Calabi-Yau. And in fact, it's not entirely clear whether it only holds for Fano surfaces or whether it's a marginal effect. Okay, I'm almost at the end of my time. So let me just say that we have checked these conjectures, or some of them are theorems. The last one is a conjecture on a large class of geometries. And here I just give the example of well, it's essentially a description that works for all del Pezzo surfaces, whether they are toric or not, except for the first two, for which there is a collection involving three blocks of sheaves with arrows only going from one block to the next, and where essentially the same ideas as for local P2 can be applied. I'm not going to explain the details of the symbols in here, but you might have seen this table on the literature on toric surfaces. So those are just the number of arrows that you have to plug in this diagram. And well, the same trick of writing the total dimension as 1 minus a negative quadratic form plus terms which are manifestly negative turns out also work in this class of geometries. This number A, B, C here are certain combinations of the data in the quiver, which satisfy actually a nice, much simpler version of the so-called Markov equation that governs these geometries, which my student Guillaume found out, which is quite pretty. Anyway, so what I want to emphasize here is that the technique works beyond the toric case, although in toric case there are well-developed methods also for generating these quivers, in particular computing sphere potentials. So I'm essentially at the end of my talk. So let me just briefly summarize. So I gave an algorithm for computing Vafa-Witten invariants of Fano surfaces, or BPS indices counting D4, D2, D0 bound states on local Calabi-Yaus. In principle, arbitrary rank using this flow tree formula, and of course using a mathematical software, because there's no way you can do this by hand. Presumably, this method should extend also to any rational surface. The rational surface is a blow-up of P2 or F0 at any number of points, and you can actually trace exceptional collection at each blow up. But it would be very interesting to generalize it to K3 surfaces or surfaces of general type. And in that case, you have to be very careful that Vafa-Witten invariants in general don't just count semi-stable sheaves, but they also include contributions from the so-called monopole branch. In other words, they count a number of Higgs bundles, and it's not clear whether quivers can capture that. The method that we have developed, in fact, bears some resemblance with some technique using scattering diagrams in the math literature. It looks like they should be equivalent to attractor flow trees, but that's something we haven't really understood. And I think the main interesting consequence, at least to my taste, is that it shows that at least for certain quivers, there is you can well, the BPS invariants indices have modular properties, or rather mock modular properties. In particular, in all these classes, you could construct a joining function where you fix some dimension vector, which would capture the D4, D2 charges, and then you allow arbitrary number unit shifts on the ranks of each the nodes. So ND0 was 1 unit at each node. And the claim is that this should have some mock modular properties, not only some, but some very precise modular properties that we know. So tentatively, we'd like to think that there is some vertex operator algebra which acts on the cohomology of these quivers, a little bit like Nakajima's action of affine A1 on Hilbert scheme of points. In fact, there is some very interesting work by Yamazaki Lee recently, which gives some natural candidate perhaps for this object. And clearly, an interesting open problem is to compute BPS indices in compact Calabi R3-folds, where non-trivial single-centered black holes are expected to occur. And while probably the quivers might not suffice, at least for general characters or charges, but some of the lessons we have learned here would hopefully be useful. So let me end here. Thank you for your attention, and remind you to mind the wall. Not everyone can cross them unscathed. Thank you.
Thank you. Questions? Actually, I have two questions.
Yeah, sorry.
Oh, yeah, it's Yao.
Sorry, I have a question. So, like, if you think about the quiver side, you have a finely tuned superpotential, but somehow to use your flow tree formula, it doesn't matter, or you can see this fine-tuned superpotential.
Yeah, it's a very good question. So indeed, most of our so in our work on with Ashok-Sen and Manshot on this Coulomb branch formula, we always assume that the superpotential was generic. Mm-hmm. But in general, you would expect some. So that was important for the conclusion that these black holes or these single certain invariants would be supported in middle cohomology. So in most of my talk, I use an alternative description using the attractor flow formula, and that does not make any assumption on the superpotential because, as I said, it's just a general solution of wall crossing. So so I think the fact that the superpotential is fine-tuned is important to ensure this vanishing of attractor indices that I explained. You could not make the same argument for a generic cubic superpotential.
Can I refine that question one more step? So I do agree that for this multi-center formula, the wall crossing solution to wall crossing, the superpotential doesn't really matter, but the intersection numbers enters. So in many of the quivers for local Calabi-Yau, we have situation where you have same number of left-going arrows as right-going arrows. Absolutely. In those situations, what are you using? Is 0 or one of the two?
Yeah, thank you. So indeed, as you said, the wall crossing formula only depends on this Dirac pairing, which is the anti-symmetric version of this Euler form, and which is not sensitive to arrows going both ways or self arrows. Right. So it turns out that for Fano surfaces, you never have this issue. The arrows only go one way.
Oh, I see. I see.
And so that's no longer true for weak Fano surfaces. So for example, for del piezo 9 or for F2. So what we notice, however, from the Vafa-Witten side is that these weak Fano surfaces have the same Vafa-Witten invariants as ordinary Fano surfaces. For example, F2 has the same BPS spectrum as F0. Marginally for Hitzebrook Fn, the spectrum only depends on n mod 2, provided you change the moduli accordingly. So the canonical class differs, but you can take care of it by adjusting the moduli. So that's not really telling you the answer. What's the prescription on the quiver side? But
so in those examples you actually displayed, you are saying you have really, arrows going one way. In all
examples where I make a strong statement, a strong claim, arrows only go one way. Yeah.
I see.
But they do have this property that the number of arrows and coming to one node is equal to the arrows leaving out, which is a property
that's
of
Calabi-Yau.
That's it's a consequence of conformality, and that implies in particular that the D0 branes are in the kernel of the intersection form, and they decouple from wall crossing. But in fact, the kernel is very large. It's not only the D0 branes, but also all but one of the D2 branes, pure D2 branes. So that means that all those BPS states whose charge lives in the kernel have BPS indices which do not suffer wall crossing whatsoever. And that's very unusual
So does that mean, for example, small n on your slide, the number of D0 brane? So you with the current setup, the counting of omega dependence on small n. Does that have a control of that or no control of that?
Well, so the BPS index only depends on the total dimension vector, which I chose to decompose in this way. I mean, clearly you could put some of that here into the starting point. That's just
I see.
So there's not much just meaning in this decomposition. It's just indicative of the fact that the modularity property should definitely appear if you construct some subset of all possible genetic functions, where you look at one particular direction in the dimension vector. But it could be that it's more general that if you take genetic functions for ranks at all possible sites, they would also have modular properties. I don't know about that.
Okay. Anybody else?
Then, if the Vafa-Witten invariant is modular, then what is the interpretation of non-holomorphic part in terms of BPS indices?
I did not hear the beginning of the question. Could you repeat?
If we admit that the Vafa-Witten invariance is modular quantity, then it seems that in the table everything seems to be holomorphic, but there is a non-holomorphic shadow. So my question is about its role in terms of BPS quivers.
Right. So so generally we expect that the non-holomorphic partition function, non-holomorphic contributions to the partition function will come from some continuum of bound states in the quiver quantum mechanics. So I don't think it has been kind of well demonstrated in the pure context of quiver gauge theory, but certainly you can analyze the quantum mechanics of the Dion electron monopole system and see that the contribution from scattering states to the Witten index, or rather to trace of -1 to the f e to the minus beta h, has non-trivial dependence on beta, which is like tau2 in this business, and produces precisely the type of non-holomorphic functions which occur in the non-holomorphic completion that you can that is necessary to ensure this modularity constraints that I explain in the work with Sergei. So I think, in fact, in the work of Piljin, Yi, and Kentaro and the third author, there was also some trace of such non-holomorphic contributions depending on the scaling of you were performing on the temperature, on the gauge couplings in the quiver quantum mechanics. I'm still not quite clear about whether there is what is the correct prescription to extract these non-holomorphic contributions from quiver quantum mechanics.
Okay. Any other questions? Comments? Or if not, the Zoom setup is going to be open basically all day until the end of the workshop. So if anybody wants to talk to anybody else here, you are very welcome to come in and talk to each other. Otherwise, unless there is a further question, let's thank Boris and close the session. Thank you.
Thank you.
Okay, so see you guys tomorrow morning.
Okay.
All right. Bye.
Boris, can I ask more?
Yeah, I'm still here. Yes.
I'm a little bit confused. So